Hey everyone, I'm going to present you spin torque building blocks article from the Nature Materials. Before diving into the article, I would like to mention about the spin torque words one by one. Let's examine the words. According to Longman Dictionary, spin means to turn around and around very quickly or to make something do this. What about the torque? Torque means the force or power that makes something turn around the central point, which is exactly matches the definition in terms of pure physics. However, spin is a motion of something, but what does it belong to? In spintronics, electrons spin around their axis. Spin is a quantum mechanical property of electrons, which makes them behave like tiny compass needles. As I show in the video, spins can be up or down, but considering the Pauli's exclusion principle, two electrons cannot be in the same orbital with the same direction of spin. So in an orbital, there cannot be up and up spin electrons, likewise down and down. Also, here with an F1 car, I just want to make an analogy about how electrons spin around their axis. You might think, okay, Doğukan, electrons spin around their axis, but what are we going to do with it? Okay, here is the why. In conventional electronics, we just use the electrons' charge to run our devices for decades. We encode and decode the binaries thanks to this property. What if we can read and write our data as ones and zeros with the spin directions of electrons? It sounds great as long as we can manipulate the spins to match our needs. Here is a tool, what we call spin torque. And the spin torque-based devices are going to non-volatile and more efficient than the conventional electronic devices due to there is no threshold for charge level. So how can we manipulate? Spin transfer torque is one of the ways of how we manipulate the spins. So how does it work? We need a three-layer sandwich structure which consists of two ferromagnets and a non-magnetic layer in a certain order. The ferromagnet at the bottom should have a fixed magnetization, while the other ferromagnet has free magnetization. When we inject electrons through the stack, the electrons get spin polarized while passing through the ferromagnet. We also know fixed magnetization and the free magnetization are not have same direction, so they are not parallel to each other. The spins will align in the direction of free magnetization due to exchange interaction. By the conservation of angular momentum, there will be a torque. We call it spin transfer torque. If we have thinner layers, the torque will increase because it relies on the current density rather than the amplitude. We have three different scenarios by adjusting the amplitude of the applied field between the states. In the first figure, we have applied field 0 or less than the coercive field, which is Hc. By injecting the current, we can obtain both states if the amplitude is enough to overcome the energy barrier. Also, this switching has mostly found in spin torque MRAMs. The second scenario appears when we equalize the applied magnetic field to the Hc. There is a stochastic switching between the states, but the antiparallel state is barely stable due to thermal fluctuations. We can also obtain frequent changes in the resistance by modulating the current. At the last scenario, the H is more than Hc. The just parallel state is stable. When the current gets more intense, the electrons will start process around the pattern since there is just one locally minimum energy level. We can have a spin torque microwave oscillators with this torque. When we inject a current through this stack that creates a sustained precession motion, we can measure this kind of resistance graph and as well as the voltage graph. That can be explained by the continuous changing spin directions due to precession, which looks like that. Let me play it again. Here is one of our example. Spin torque wave emitter. We use direct current again, but this time the stack is different. There is a point contact, instead bigger one, which is going to help to observe the wave emission thanks to locally sustained precession. And we also obtain this kind of graphs, this kind of figure. So, spin torque microwave detectors need an AC current frequency close to the magnetization resonance frequency. Once the resistance and the current oscillate synchronized, it leads to rectified voltage. This is possible with the direction changes of spin torque thanks to AC current. Spin torque memristors have the same functionality just like the ordinary memristors. We are using a pulsed current to change the place of the domain wall. Therefore, we obtain different resistances. The position of the domain wall distributes the parallel and the antiparallel magnetization states. So, even without injecting current continuously, we obtain different resistances. How to improve spin torque devices? As I mentioned in the previous slides, if we have thinner layers, we can obtain the same force of torque, even decreasing the current. This is also going to reduce the power consumption. Integration of magnetic anisotropy materials in spin torque MRAMs is another solution. Other than the material-based solutions, we can assist spin torque by additional physical phenomena, which are electric field effects on magnetization and the spin orbit torque. Here is the SWOT analysis of spin torque-based devices comparing to conventional electronic devices. Thanks to read and write works use the magnetic states of electrons, there is no need to consume huge amount of power. Also, their non-volatility relies on the use of magnetic states. And the exceptional latency for the spin torque MRAMs compared to DRAMs, which is going to make your devices faster. One of the biggest downsides is data loss is possible in strong magnetic fields, hot places, and under high pressures since we work with ferromagnets. One of the opportunities, microchip industry still cannot meet the demand during this period, which is COVID. Releasing the spin torque-based devices to more areas can make them popular. And there is no threats available yet. In conclusion, we are going to see more spin torque-based devices day by day. Thanks for your attention.